Hey, in this tutorial we're looking at section 13.2 on position vectors as functions of time. Okay, so we can talk about this in terms of parametric equations. So that remember that as a particle moves, its x and y positions can be defined in terms of time, t. So we can say x is equal to x of t and y is equal to y of t. So this means that the position vector of a particle is given by r of t equals xi plus yj, or, and the way that we'll use it more often, is r of t equals x of ti plus y of tj. Okay? Using that form there, we can find the position of the particle at a given time t, or find the time when a particle is closest to the origin. We can also do work on collision problems. So for two particles to collide, they must be in the same position at the same time. Okay? Particle paths may cross, okay, so they could be at the same position but at different times. And we can find the distance between particles at a particular time. Okay, so we'll have a look at some of the work examples for this section. So work example 1, we're given the position vector r of t equals 3t minus 4i plus 4t minus 3j for t is larger than or equal to 0. And we need to find the distance of the particle from the origin when t equals 2. Okay, so all we need to do is sub t equals 2 into here. So we can say, well, r of 2 is equal to 3 times 2 minus 4i plus 4 times 2 minus 3j. Okay, so that means we're going to get 2i plus 5j. 5j. Okay, and what we need to do though, okay, is at the moment we know that it's actually at the point 2, 5 that we need the distance from the origin. Okay, so essentially what we're doing is Pythagoras' theorem. Okay, so we're saying the modulus of R2 is our distance, and that's equal to the square root of 2 squared plus 5 squared, okay, which is equal to the square root of 29. Okay, so that's all there is for that one there. Okay, and we'll have a look at part B now, okay, which is wanting us to find the distance of the particle from the origin at any time t. Okay, so at any time, really, we're just going to be taking the modulus of it and saying that we've got the modulus of r of t equals the square root of 3t minus 4 squared plus 4t minus 3 squared. Okay, so we can expand that out. We'll have 9t minus 24, so 9t squared minus 24t plus 16 plus 16t squared minus 24t plus 9. Okay, we can collect our like terms. Okay, so we're going to get 25t squared minus 48t, okay, and plus 25. Okay, so that would be our distance at any time t. Okay, so we'll keep moving on now. We've got one last part for this worked example, which is find the closest distance of the particle from the origin. Okay, so the particle will be closest to the origin when we've got our derivative of our distance is equal to 0. Right? So what we need to do is we can think about this and say, well, modulus of r of t is our 25t squared minus 48t plus 25 to the power of half. Okay, so we need to use we need to find the derivative of this. So d of r of t dt. Okay, so we need to use the chain rule here. So we'll have a half, and we've got to bring down our power times by the derivative of what's in here, which is 50t minus 48. okay, times by what we've got in here, 25t squared minus 48t plus 25 to the power of negative a half. Okay, and we can simplify that, okay, because we can run our half through here and make it 25t minus 24, okay, over our square root of 25t squared minus 48t plus 25. Okay, and we're going to set that equal to 0. Okay, so say we could multiply it out and our bottom line would disappear. So really we can say 0 equals 25, t take 24. Okay, so t is going to equal 24 on 25. That's the time that we get our minimum distance. What we need to do is actually now find what that distance is. Okay, so what we can do is we can sub in, okay, now our 24 into our equation. Okay, so what they do is they sub it in to here, okay, and then use this function here. We could also, though, we know our modulus for any time is this function here, so I could also do that and get the same answer. So we'll say, well, r of 24 on 25, okay, is equal to 3 times our 24 on 25 minus 4i plus 4 times our 24 on 25 minus 3j. Okay, so that's equal to minus 28 on 25 I plus 21 on 25 j. Okay, so then our modulus of 24 on 25 equal to the square root of our minus 28 on 25 squared plus our 21 on 25 squared. Okay, when we do that, we get a result of, okay, they simplify this a bit and say that we've got 1 on 25 times the square root of 1225, okay, which simplifies right down to 7 on 5. Okay, so the minimum distance is equal to 7 on 5 units. Okay, so we'll keep moving on. We've got another worked example to have a look at. Okay, which is the worked example 2. So we're given two position vectors, a of t, which is 3t minus 8i plus t squared minus 18. That should be t, not an I. Okay, minus 18 t plus 87j, and b of t is 20 minus t I plus 2t minus 4j. Okay, and again, where 4t is larger than or equal to 0. Okay, so for part A, what we need to do is find when and where the particles collide. Okay, so if they're going to be in the same position, then our I components and our j components have to be equal. Okay, so what we can do is we can set our coefficient of I and j to be equal. So say 3t minus 8 equals 20 minus t. Okay, so we can rearrange this and get that 4t equals 28. So t is going to equal 7. Okay, so then what we need to do is make these equal to each other as well. Well, t squared minus 18t plus 87, okay, is equal to 2t minus 4. Okay, so we can rearrange that and get t squared minus 20t plus 91 equals 0. Okay, and we can in fact factorise that and make it t minus 7, t minus 13 equals 0. Therefore, t equals 7 or 13. Okay, so we have a common solution of t equals 7. Okay, so therefore r of B at t equals 7. So after 7 seconds they will collide. Okay. So what we need to do now though is actually find where that position is. Okay. Now of course we know that they're going to collide at that time. Okay. So we don't need to actually find it for both of them, we can just find it for one of them. Okay. The easier one would be of course to look at this one. Okay, so we can say B of 7, okay, equals 20 minus 7i plus 2 times 7 minus 4j. Okay, so they're going to collide at the position 13i plus 10j. Okay, so and so that the coordinates at that point, of course, is 13, 10. Okay, so the point 13, 10 is where they'll collide. Okay, so in part B, we need to find where their paths cross. Okay, so the particles' paths cross at different values of t. Okay, so what we need to do here, okay, is actually introduce a different parameter s. Okay, so what we do, say, well, r a of s, okay, is equal to our 3s minus 8i plus s squared minus 18s plus 87j. Okay, and we can leave at the moment our RB of t alone. Okay, so what we then do, okay, is again look at solving our coefficients of I. Okay, so we can say we've got 3s minus 8 equals 20 minus t. Okay, so what we can do is rearrange this for t, and we get t equals 20 minus 3s. Okay, and again we can do the same thing with our other parts as well, and say that we've got our s squared minus 18s plus 87 is equal to 2t minus 4. Okay, so we know, however, though, that t equals our 20 minus 3s. Okay, so we can sub that in for t here, and we'll get s squared minus 18s plus 87 equal to 2 outside of 20 minus 3s minus 4. Okay, and we can expand out those brackets. Okay, to get our sorry, that should be 28. 28, sorry. Just made that little mistake there. Okay, because we get then that it's 56 minus 6s minus 4. Okay, and we can collect like terms, okay, which means we get s squared, okay, minus 12s plus 35 is equaling 0. Okay, we can factorise that, and we get s minus 5 and s minus 7 equaling 0. Okay, so we can say, well, s equals 5 or s equals 7. Okay, so we evaluate the position vectors at the required time. Okay, but we know that when s equals 7, okay, that's going to be when our particles collided before. Okay, so we only need to worry about it at 5. So now what we do is we use this s equals 5 value, okay, and sub it back in to our r of a, okay, or our r of b. It doesn't really matter, okay, because again we're going to get the same answer. So we'll use our r of b again. R of b of 5 equals our 20 minus 5. Sorry, I'm skipping a step here. Okay, we don't just sub straight back in, sorry, because we're not subbing back in for t, we're subbing back in for s of 5. So what we need to do is actually work out what our corresponding time is. so when our S equals 5, well, T is going to equal 28 minus 3 times our 5. So our T is going to equal 13. Right? So we're actually subbing in our 13. So we can say our RB of T, right, is equal to our 20 minus 13 I plus 2 times 13 minus 4 J, right, which is equal to 7I plus 22J. So it'll be the time when their paths cross, okay, is T equals 13, and it's at the point 722. Okay? So you'll note that it was actually the same as our other time that we had earlier. Okay? So we've got one last part, which is the distance between the particles when T equals 10. Okay, so what we need to do for this, okay, is we need to work out our R of 10 for both these functions. So and say our RA of 10, okay, is going to be equal to our 3 times 10 minus 8I plus 10 squared minus 18 times 10 plus 87 J. Okay, and when we simplify that, we get 22I plus 7J. Okay, and when we do it for our RB of 10, okay, we get our 20 minus 10I plus 2 times 10 minus 4J, okay, which gives us 10I plus 16J. So what we do here, okay, is find the difference between these two. Okay, so what we do is we say RA of 10 minus our RB of 10, okay, which means we've got then our 22I plus 7J minus our 10I plus 16J, okay, which means, okay, 22 take 10 gives us our 12I, 7 take 16 gives us minus 9J. Okay, and then what we can do is find the magnitude of this. Okay, so that means that we go the square root of 12 squared, okay, plus minus 9 squared. Okay, that gives us a value of the square root of 225, which is 15. Okay, so that means that the distance, okay, between our two particles, okay, at a time t equals 10 is 15 units. Okay, so a little bit of work with this stuff. Okay, probably been a little bit of a while since we've seen some of our vector equations and our position vectors, things like that. Okay, so you may need to brush up on a little bit of those skills from our earlier work, but hopefully you won't have too much trouble getting through the questions.